Hello everyone, my name is Chanjun Lee and I'm thrilled to share with you our research titled Symmetric Policy Design for Lag Locomotion. Today, I'll walk you through how we've enabled quadruped robots to navigate diverse terrains using only proprioceptive sensors, no cameras or LiDAR, through two key innovations, Symmetric Policy Design and Grid Terrain Curriculum. Quadruped robots have made incredible strides in locomotion, largely thanks to reinforcement learning. However, a significant challenge remains. How do we ensure robust navigation across complex terrains without relying on expensive and fragile extraceptive sensors? This is crucial because sensor failures can render a robot inoperative in real-world scenarios. Our approach focuses on proprioceptive data alone. A common strategy here is to use historical observations to estimate the robot's state, but this introduces the curse of dimensionality, making learning inefficient. While past work leaned on representation learning to address this, we took a different path, leveraging the robot's natural symmetry and a tailored training curriculum. To set the stage, let's look at quadruped locomotion. These robots have 12 actuators, 3 per leg, controlled via a PD controller. They rely on an inertia measurement unit for angular velocity and orientation, and joint encoders for position and velocity data. The goal is simple yet challenging. Follow a command velocity defined by linear velocities in the x and y directions and an angular velocity around the z-axis. Reinforcement learning is a methodology to optimize the action selection to maximize the sum of rewards. Policy is a function that takes observation and outputs action, usually designed by neural network. This is our overview. SPD policy is trained using PPO algorithm. While our simulator runs on 200 Hz, our policy updates PD target on 50 Hz. For robot, we used Unitary A1 quadruped robot. Let's dive into how we built this framework. First, the environment setup. Our observation space includes angular velocity, projected gravity, command velocities, joint states, previous actions, and an estimated linear velocity, computed by a neural network from historical observations, since we can't measure it directly. Actions are target positions for the 12 actuators, and the reward function balances velocity tracking with penalties for excessive motion or instability. The details are presented on appendix. Now, symmetric policy design. The core idea is that quadruped robots are structurally symmetric. We define an inversion operator, denoted by a superscript f, that flips left and right information. For example, a velocity vector vx, vy, vz becomes vx minus vy, vz. Imagine an optimal trajectory of a robot climbing stairs. If we invert that trajectory, flipping action and states, it should remain optimal for a mirrored environment. This implies that an optimal policy exists that satisfies this symmetry condition. The flipped action under an unflipped observation is equal to action under a flipped observation. How do we enforce this? We split the observation into left-based and right-based components. The left-based observation is the standard input, while the right-based is its flipped version. A neural network GUI processes the left-based historical observation to produce the left action, and the same network processes the flipped observation for the right action. The structure inherently satisfies the symmetry condition, cutting down the exploration space and boosting learning efficiency without compromising capability. Previous curricula adjusted terrain difficulty based on overall performance, often hiding weakness in specific velocity ranges. We address this by dividing the command velocity space into an 8x8 grid, where robots trained in assigned cells with local command sampling when grid on is active, or globally otherwise for variety. We measure the following rate: how well robots track commands, and increase terrain difficulty if it exceeds 0.7 or reduce it if below 0.5, balancing learning across velocities. On to results. We trained our policies in Isaac Sim using PPO. The learning curve tells the story. SPD consistently outperforms the baseline, which higher episode returns and faster progression through terrain levels. For evaluation, we tested 3 setups: A1 with SPD, A1 without SPD, and A1 with a baseline curriculum. We measured the following rate across terrain types and levels. As you can see, in high-level difficult terrains, it showed approximately 1.5 times to 2.0 times better performance. Let's see in action. The video shows our robot tackling stairs, adapting its gates seamlessly. In this work, we've introduced symmetric policy design and grid terrain curriculum to tackle lagged locomotion on complex terrains, using only proprioceptive data. No representation learning needed. This method leverages symmetry and structured training to deliver robust performance. We opened all codes and materials on here. Here are appendix and references. Thank you.